Good afternoon, good morning, good evening, everybody. I hope you've all had a very good afternoon and you can see and both hear myself and Sarah. If you can't hear or see us, then please put something in the chat box. A few technical issues before we started, but we should all be up together now. I would like to, first of all, thank everyone for joining us on today's Advancing X-ray Inspection with Artificial Intelligence, an innovative denoising technology webinar. I'm going to introduce our presenter. Sarah has a PhD and is the sales engineer for industrial applications at Hamamatsu. And Sarah has been with Hamamatsu Photonics Italy since the beginning of 2022. She's responsible for industrial X-ray, NDT spectroscopy and radiation monitoring markets. And prior to working at Hamamatsu, Sarah completed a PhD in nuclear physics with a project on gamma ray spectroscopy and radiation detectors. Hi there, Sarah.
Hi there, Rob.
I am going to run through a few house rules first of all. Please put any questions you have into the chat box that you have at the bottom of your dashboard. At the end of Sarah's presentation, we'll try and get through as many of those as we possibly can. If for any reason we don't get the chance to answer your question, don't worry, all questions are recorded and someone from Hamamatsu will get back to you directly. Just to let you know also that this webinar is recorded and there will be a recording available from the optics.org website in about 24 hours time. So if you do miss anything or have to dip away, you can always catch the recording there. And of course, we'll try and make sure that we send out a copy to everyone that has decided to join us today. So thank you very much. Without any further hesitation, I'm going to hand over to Sarah for today's presentation. I'm controlling the slides, so if I make any mistakes, Sarah will sure point me out and make sure we keep on track. Okay, Sarah, over to you.
Thank you. Good morning and good evening, everyone. Thanks, Rob, for the introduction, and thanks to optics.org to host this webinar. On behalf of Hamamatsu Photonics, today I will be your guide to explore an innovative application of artificial intelligence. So artificial intelligence has become a real hot topic in our everyday life. And today we will see it combined with simulations to remove noise from X-ray images. So let's quickly go through the overview of this presentation. I will introduce Hamamatsu Photonics company before entering into the details of basics about noise nature and X-ray detection. After that, I will explain you how our new artificial intelligence denoising technology works, decomposing it into its building blocks, which are the deep learning algorithms and the X-ray imaging simulations. At the end of the presentation, I will then give you some information about the validation of the technique and how and which type of advantages it brings to your to the X-ray inspection. So, for those of you who do not know us yet, Hamamatsu Photonics is a Japanese company based in Hamamatsu City in Japan, who produces and commercializes components and systems related to optoelectronics since 1953. We have over 15,000 products in our lineup, and we are adding new products every year related to a lot of different applications. So next slide, please. Our products are involved in academic research, like high energy physics or life sciences applications, but we also provide products for pharmaceutical applications, medical field, passing through automotive and industrial applications. At the basis of our company philosophy is to improve and to advance photonics. So what I'm going to discuss with you today is a step in this direction. But let's start with a very fundamental question. So what is noise? I just wanted to put here in this slide a very simple and clear definition of what noise is. But since I found so many different types of definitions, from very practical ones to very complex ones, I just couldn't put a very simple definition here. So let's start from something that all of us experiences and everyone knows. So noise can be an unwanted or unpleasant or loud sound. But if we take a closer look to the world outside, noise in reality characterizes all physical systems in nature. So the actual um, definition of noise that we are going to use in this presentation is that noise is an unintended fluctuation of output. In general, noise, since it is a feature of all physical systems, from biological systems to electronic systems, people usually want to measure noise because it can give you information about a system, about how a system is built. But in this presentation and today, we do not want to measure noise, we want to get rid of it. But why? Noise, when you are acquiring a measurement or you are making an analysis, a fluctuation of the output can lead you to a wrong result. And for example, it can trigger a false or positive negative, a false positive or false negative result, for example, in fluorescence measurements. Or, so please go ahead, Rob. Thank you. Again, a fluctuation of the output can lead to an error in measuring a distance, for example, with an autonomous vehicle, or it can lead to an error in a transcription when you are considering a light communication. But the most similar example to what we are going to discuss today is that due to noise, we can get a bad image with the camera, especially when we are acquiring images in a low light conditions or in at very high speed. Please go on. Okay, so we usually think about images with visible light, but visible light is just a tiny, tiny portion of the entire electromagnetic spectrum. In particular, the electromagnetic spectrum is composed of mainly invisible light, for example, infrared light or ultraviolet light. Today, we are going to concentrate on the left part of the electromagnetic spectrum, where we have X-rays. And like visible light, we can acquire X-ray images. So how can we do that? Next slide, please. So how X-rays work? We have an X-ray emitter. X-rays encounter an object, and in the object, they can be absorbed, scattered, or even transmitted. The quantity of X-rays transmitted and absorbed by the object depends on some features of the object itself, like its density, the thickness, or the atomic number. And by measuring the transmitted X-rays, we can acquire X-ray images or radiographies, and for example, observe contaminants or defects inside the product. Next slide. But let's take a step back and understand how X-rays are detected. First of all, the X-rays are converted into visible light in a scintillator material. So next. I have a kind of, thank you. In the scintillator material, which re-emits visible light. Then the visible light is converted into an electric signal, for example, in a photodiode, in this case here. And after that, the electrical signal is collected by an electrical circuit, which transforms the electrical signal, eventually digitalizes it, and at the end, what we obtain is an X-ray image. Next slide, please. So, now that we have common understanding of what noise is and how X-rays work, we can talk about the technology Hamamatsu has developed to remove noise from X-ray images, exploiting artificial intelligence. First of all, X-ray images quality can be affected by noise, especially when acquired in low-dose conditions or at very high speed. How much noise we are going to have in the image depends on many factors, like X-ray conditions or the type of object we are inspecting, or again, the type of detection system we are using. To remove the noise, we should in principle experimentally know all the possible conditions, and you can immediately understand this would take a huge amount of time and effort. So the solution Hamamatsu Photonics found is to use an X-ray simulations to generate all the necessary images in the various conditions to be used to train artificial intelligence algorithms to identify the noise components. You do not need to acquire images one by one anymore, because simulations can quickly generate both signal and noise components that build the image. However, given a certain signal level, like in the 3 images here that all have the same signal level, we can have more or less noise intended as smaller or larger fluctuations, and this makes it more difficult to teach an algorithm how to remove noise. To solve this problem, we introduced the so-called noise map, which is a representation of noise fluctuations relative to the signal component. Noise fluctuations, in fact, can be calculated with this complex formula here on the top right, and then used together with simulated images to train artificial intelligence algorithms. In this way, we can achieve the best noise reduction in all the possible conditions. Of course, the technique should be validated. So, for example, we can use test charts to validate first the technique. We can use test charts with different thicknesses, simulating, for example, different imaging conditions at the same time inside the same image. So the denoising technology is applied to the raw image, to the real acquired image, and what we do is to verify that the noise removal is effective in all the regions of the image. Finally, we should test the technique with real samples, like raw meat in this case, and this is crucial to be sure that we are removing only the noise component and not the signal that we want to retain as it carries the real information. These tests not only validate the technique, but also show that exploiting our artificial intelligence-based denoising technology, we can achieve better results in contaminants detection, identifying contaminants that were not visible with standard techniques. So the denoising technology comes in a software package, which is closely related to Hamamatsu hardware, because you can understand that we are quite good at simulating our own hardware. And with this combination of hardware and software, we can achieve the best performance. Okay, so this is a very general overview of the technique. And what we are going to do now is to enter more into the details of the building blocks of the technology, starting from the deep learning algorithms. Okay, next slide. So artificial intelligence is a branch of computer science focused on creating systems capable of performing tasks that typically require human intelligence. These tasks include, for example, problem solving, understanding natural languages, recognizing difficult patterns, and making decisions. And artificial intelligence systems could range from very simple algorithms to sophisticated neural networks designed to mimic the human brain's functionality. And deep learning is a subset of artificial intelligence, which involves using neural networks with many layers, from which the definition deep, to analyze and interpret complex data. And it enables machines to learn from vast amount of data by identifying intricate patterns and correlations. And deep learning is commonly used in image and speech recognition, for example, or autonomous driving. And nowadays, it has become a critical component of modern artificial intelligence applications. Next slide, please. when you need to use a deep learning algorithm, you have to train the algorithm first. And to do it, you need two data sets. The first data set is the input data set. And when we want to remove noise from X-ray images, what we are going to input is the measured image. On the other side, we need a teacher data set to guide the algorithm and understand what we want it to identify. And in this case, what we want to identify is the noise component, which should be then removed from the image. And what you can immediately understand is that when you have a trained data set, a trained algorithm, and you apply it to remove noise from an X-ray, a general X-ray image, this type of approach can be used only if the inspection parameters are exactly the same as the ones used to train the AI. Otherwise, it cannot be applied directly. So, what you can understand is that in principle, you need to train the algorithm in all the possible conditions available. So please go ahead. Okay, so you need to train the algorithm with all these possible conditions, which depend on the product. It depends on the X-ray source, on the type of the detection, and you can easily understand this takes a lot of time and a huge amount of data that cannot be easily acquired. Next slide. So this is where our X-ray simulation technology comes to help. So Hamamatsu Photonics has developed a proprietary technique for three-dimensional simulations for X-ray imaging based on 4 points. The first point is to simulate, so the 4 points are X-ray emission, transmission, absorption or conversion, and detection. So as the first point, we need to simulate the X-ray emission spectrum. Next slide, please. So here on the right, you can see that the red curve is the incident X-ray spectrum, energy spectrum, which is associated to X-rays that didn't interact yet with the material that we want to inspect. The second step of the simulation, which is in the next slide, is to simulate the transmitted X-rays. So the X-ray spectrum after it has interacted with the object, because interacting, some X-rays are absorbed, some of them are scattered, so we do not retain the entire X-ray spectrum. The third step is the scintillator response. The scintillator material has its own probability of absorbing X-rays. It has its own efficiency in converting X-rays into visible light. Please go on. Again, perfect. And please go back just one, again. This is perfect. So when re-emitting visible light, the scintillator has a preferential direction. So you can imagine that when the emitted visible light is in a broad cone or even in an isotropic direction, this light can be detected by multiple pixels inside the sensor. So it introduces a worsening into the resolution of the image and a blur. Next again, thank you. The fourth point is the sensor response, because each sensor has its own sensitivity and it has an intrinsic resolution related to the pixel size of the sensor. And in addition, each sensor is associated to fluctuations of the electronics. So these are the 4 points related to the X-ray simulation technology. And please go to the next slide. Thank you. We need to validate our simulations. To do so, we first compare measured images, so real images, with the simulated ones. We test a number of parameters, and here I just listed 3 of them because are quite straightforward to understand. So we test contrast. So it is the gray level associated to each part of the image that we are inspecting. The noise level, so how much noise that we have and how big are the fluctuations. And the final resolution, which is associated to many factors, between which we have the initial X-ray spectrum emitted from the X-ray source, the scintillator response, and the resolution of the sensor itself. Okay, so with this technology, you can understand that we can quickly simulate and generate a huge amount of data, and this data can be used to train artificial intelligence algorithms. Okay, next slide, please. So now we have the 2 building blocks of our artificial intelligence denoising technology, and to obtain it, we put them all together. We have in the middle our deep learning algorithm, and we give, instead of giving real measured input images, we just give it simulated images. And as a teacher training dataset, we use the simulated noise images. But this is not all. We need to add some information. Please, next. Okay, again. Okay, so what we need to add to this approach is the noise map. The noise map represents the fluctuations of noise with respect to the signal. Please go ahead. Okay, so the noise map, for those of you who are more confident with mathematical concepts, is the standard deviation of noise. So putting together simulated images, the noise map for the input data, and the simulated teacher noise, we can train the algorithm. And once the algorithm is trained, we can apply it to remove noise from real measured images. Okay, next slide. And now we come to the technology validation. One of the most challenging points is to be sure that we are removing noise effectively in all brightness conditions. And to simulate this type of condition, we can use test charts with increasing thickness and fake contaminants on top. Please go back. Thank you. So we acquire an X-ray image, a raw image of the test chart. We apply our denoising technology, and here on the right, you see that we can effectively remove noise from all the parts of the image, either in the top part, where we have a lower thickness of the test chart, and therefore we have a higher brightness and a better signal to noise, but also in the lower part of the image where we have thicker test charts. So X-rays, less X-rays pass through the material, and we have a lower brightness and a lower signal to noise ratio. Next slide. Finally, we have to test the technology with real samples. In this case, for example, I can show you a raw pork meat. Again, we acquire a raw image of the raw pork, then we apply the algorithm, and what I can show you here on the right is that the noise component that we are removing, and you can simply see that we are extracting only noise, and we are not removing any signal component, because this is what we want to retain, because it contains the actual information that we want to keep. So if we take a closer look to the area of the image that in this case contains some contaminants, please go ahead to the next slide. Okay, next slide. If we take a closer look, we can see that on the left side we have the raw image, and on the right we have the denoised image. You can see that even with a very simple thresholding technique in the denoised image, we can see an improvement in contaminants detection that were not visible before in the raw image because of a bad signal to noise ratio. Next. We are almost at the end of this presentation, and I just would like to give you some final remarks. First of all, I told you before that this software is strongly linked to our hardware. And in particular, the first type of hardware Hamamatsu Photonics would like to address is our flat panel sensors, so two-dimensional detectors. And second, this technology is still under development, so it has not been commercialized yet. So you have to be patient and wait a bit more before using it into your inspection machines. But don't be afraid. Please do not hesitate to contact us because our team is willing to help you and give you more details. Okay, so I really would like to thank you all for your participation, and I hope you are thrilled with this kind of new technology. And I would like to thank you all for your attention, and I am now available for your questions.
Hi, Sarah. Thank you so much for giving that presentation. It couldn't have been easy having to have me lead you through the slides. So thank you very much for doing that. We have had a few questions in, and so I'm going to plow through those as best as I can. First of all, could you we've got one here. How do you simulate images in case you cannot know the exact shape structure of the product?
Okay, so this is one of the most challenging parts of this technology. In principle, when you do not know exactly the structure of a product, you usually use test charts, or you can simulate the structure by using already available coefficients, absorption coefficients for X-rays. For example, the pork meat or the chicken meat can be assimilated to absorption coefficients or of some kind of acrylic resins. So you can simulate the product using already known absorption coefficients. And this is what you usually do. And of course, using test charts is one of the best ways. For example, using test charts with increasing thickness to simulate all the possible conditions is usually what it is done.
Okay, and also we've got another question here. Does your algorithm automatically identify product defects?
Okay, so in this case, we are not identifying defects. We are just removing noise because usually customers would like to tailor their own software for the contaminants detection, because it really depends on which type of defect or contaminants you would like to measure. You can imagine that it is completely different if you want to find out a piece of glass in a jar or a crack inside a die cast.
Right, okay. And is this technique suitable for any type of product or specific for a particular category of objects, you know, food, plastics, that sort of thing?
In principle, so at the beginning, this type of technology has been tested by our Japanese colleagues and engineers with raw food, for example, the pork meat or chicken meat that I showed you before. But in general, since we have this strong simulation technology, we can simulate whatever we like. So we can train the algorithms with all the possible products that we want.
Okay. Also, we have another one here. What are the main challenges when you have multi-material components, as absorption, transmission could be quite different between materials?
Yeah, this is almost linked to the first question. So the main point stays in the simulation technology, because of course the algorithm can be trained with whatever we like, but the difficult part is in the simulation part. So if you have multi-material, you have to understand all the absorption coefficients of the parts composing the product, and then build the simulation and tailor the simulation on the type of product that you really want to measure.
Okay, so this probably leads slightly on to the next question. How do you see the contaminants? So for a meat database, data set, for example, in grayscale images?
Yeah, the contaminants are usually seen because they have a different gray level with respect to the surrounding. So, for example, in the meat that we saw before, we had that small balls. For example, they can be glass balls or metallic ones, and they have a different gray level. So, for example, if we have the surrounding material at a certain gray level and the contaminant at a different gray level, putting a simple threshold can cut out what it is actually the material that we want to keep, and you can highlight the contaminants that you want to identify. Sometimes it can be difficult because sometimes the gray levels are too close to each other. So sometimes it's better to identify contaminants based on the shape, and you can train algorithms in this way.
Okay, and you mentioned in the presentation sort of the statistical noise. Are you able to remove noise, statistical noise, and also structural noise?
Yes. So in the simulation part, we take into account all the types of noises coming from the different parts. So we can have noise due to the blur of the scintillator response. We can have electronic shot noise. And of course, we can have dark counts, statistical noise in general. So in the simulation, all these types of noise enter because we simulate all the different parts that can generate noise. And we can take into account the noise map, which is mostly related to the signal. And we can train the algorithm to remove all these components.
Okay. Can the software also handle scatter radiation?
Sorry, could you repeat, please?
Can the software also handle scatter radiation?
Okay, I'm not quite sure about this. In principle, yes, because what we do is to simulate both the initial spectrum and the transmitted spectrum. So in a way, the transmitted spectrum already takes into account that some X-rays has been scattered. But of course, some of the scattered X-rays can come to the sensor. So I'm not sure exactly about this point. We should ask our Japanese colleagues who developed the algorithm. But this is a very nice question. So please come back to us and ask again.
Okay. So we've got a few more here, if you don't mind. Could you actually please just explain the training procedure of the neural network again?
Yes. Okay. So the neural network receives as input the images that we want to process. So we have just standard images, and on the other side, we just give a teacher data set to explain to the algorithm what is our goal. So when we are dealing with the simulation, we simulate together the images and the training and the teacher noise. And in the middle, what happens is just an iterative process. So we give an image, we pass it through the algorithm, and at the end, we check that we obtained what we wanted. If this is not the case, we restart from the beginning, changing some parameters inside of the neural network until we obtain what we wanted. So this is the entire procedure.
Okay.
I hope it's clearer now.
Yes, I'm sure people will want to watch this again anyway, so they can always catch up with it again.
Yeah, I think it's quite a difficult part to understand in the beginning.
Oh, I've no doubt. One thing that a few people have asked is, does the customer need to train the algorithm?
In general, our engineers will train the algorithm for you. So you just tell us which type of product you would like to inspect, and we will train the algorithm for you.
Excellent.
At least in the beginning, because we are still in the development phase.
Yes, absolutely. I'm going to ask probably just one more question here before we have to wrap things up. Could I ask, have you published the results already?
Yes, we published one article or a couple of articles, but they are not kind of our scientific articles. They are just divulgative articles. You can find them online, maybe also on our website. So it's more or less it's written what I explained to you here in this webinar.
Okay. Or maybe we can squeeze one more question in.
Okay.
Have you observed a better IQI detectably, single or double IQI?
So I'm not sure about this question. So probably I can we can answer at the end of the webinar. If you can send us your specific question, we will answer afterward.
No problem at all. Okay. Well, I think that's probably all we have time for right now, Sarah. I know we've bombarded you with quite a few questions, and it's been a full-on
We'll try
afternoon.
to answer your questions afterwards.
Excellent. Well, everybody, first of all, I'd like to thank Sarah for giving an excellent presentation this afternoon, or this morning, or this evening, wherever you may be. I'd also like to thank you all as attendees for joining us today. We are hosting quite a few different webinars throughout the year on optics.org, and if you've missed any of Hamamatsu's previous webinars, you can find them on the optics.org website. In fact, Zara did one very recently on SWIR technology, so that was very good. And we will hope to catch up with you all in the not too distant future. Just before I go, Sarah, do you know of any upcoming shows or exhibitions or conferences where we can find you?
Yes, we have few exhibitions throughout Europe that we are going to have in a few months. So if you go on, you can find the list.
Ah, there we go.
Okay. Yeah, so we will be in Denmark, Sweden, and Italy in October and November. So if you want to get in touch with us, please do not hesitate to come to these exhibitions.
Excellent. Well, once again, it just takes me to thank everybody for joining us today. I hope you found it a very useful presentation. And just as a reminder, you can catch a recording of this webinar on the optics.org website in about 24 hours. So thank you very much for your time and enjoy the rest of your day. Cheers. Bye-bye.